talk about is a sampling distribution. And you've got some definitions to fill in here. A probability distribution for the sample statistic. That's what a sampling distribution is. It can be for the mean of a population. It can be for the standard deviation. It can be for other characteristics that are statistics, but mostly we deal with mean, standard deviation, and proportion. It's based on all possible random samples of the same size from the same population. The key thing is that it has to be samples of the same size. So our first example is going to be, we're going to use the experiment of rolling a die. And in order that we can see the population, I listed it for you. The population, if you roll a single die, is 1, 2, 3, 4, 5, 6. We're going to roll that single die twice to collect samples of 2. So we're going to select samples with 2 elements each in sequence with replacement. Now obviously with a die it's with replacement because you don't lose a 2 just because it landed 2 face up this time. It can land up face up with a 2 the next roll as well. So this is the sample means that we're going to construct. And at this point I'm going to switch over to the notes and talk to you about how that works. So here's what might happen. If we roll a die twice, the first roll might be a 1. And it is possible that the second roll is also a 1. And if we got a 1 and a 1, 1 plus 1 is 2 divided by the 2 rolls, what we're going to get is a mean X bar of 1. I think I can slide this back and forth so you can see this better. Now it's also possible that we would roll a 1 followed by a 2. So if you add the 1 to the 2 you get 3, and 3 divided by 2 is 1.5. Or you could have gotten a 1 and the second roll might have been a 3. 1 plus 3 is 4. 4 divided by 2 is 2. Or you could have gotten a 1 and then a 4, which gives you 5, and 5 divided by 2 is 2.5. Or you could have gotten a 1 and a 5, which is 6 when you add them together, divided by 2 is 3. And if you rolled a 1 followed by a 6, that's a sum of 7 divided by 2 is 3.5. So what we're doing here is we're taking samples of size 2 from this population and finding X bar. So we're going to continue to do that for all different size samples. Now the only thing that's going to be different in the next group is the first die isn't going to be a 1. We're going to assume that it was a 2. So if you rolled a 2 and then a 1, that's the same mean as if you rolled a 1 and then a 2, it's a 1.5. And if you rolled a 2 and then another 2, that's 4 divided by 2 is 2. And if you rolled a 2 followed by a 3, that sum is 5. And 5 divided by 2 is 2.5. And then if you rolled a 2 and a 4, that's 6. And 6 divided by 4 is 3. And if you rolled a 2 and a 5, that's 7 divided by 2 is 3.5. And then a 1 plus a 2 plus a 6 would be 8. And the mean then would be 4. Now if you rolled a 3 first, three plus 1 is equal to 4, just like 1 plus 3 was equal to 4, and when you divide that by 2, you get 2. And 3 plus 2 is 5, just like 2 plus 3 was 5, and 5 divided by 2 is 2.5. And then 3 plus 3 is 6, and 6 divided by 2 is 3. 3 plus 4 is 7, divided by 2 is 3.5. 3 plus 5 is 8, divided by 2 is 4. And 3 plus 6 is 9, divided by 2 is 4.5. And then we'll start with 4. So if you rolled a 4 on the first roll, and then you rolled a 1, your mean would be 2.5. And if you rolled a 2, your mean would be 3. And if you rolled a 3, your mean would be 3.5. And if you rolled a 4, the mean would be 4. And if you roll a 5, the mean is 4.5. And if you roll a 6, your mean is 5. Now, if anybody gets lost as we go through these, say something and I'll slow down. But you're basically repeating a pattern here. So if your first roll is a 5, and you roll a 1 on the second roll, your mean is 3. If you roll a 2, it's 3.5. If you roll a 3, it's 4. And if your second roll is a 4, it's 4.5. And if your second roll is a 5, then your mean is a 5. And if your second roll is a 6, your mean is 5.5. So our last option for a first roll is a 6. And a 6 followed by 1 has a mean of 3.5. And a 6 followed by a 2 has a mean of 4. And a 6 followed by a 3 has a mean of 4.5. And a 6 followed by a 4 has a mean of 5. A 6 followed by a 5 has a mean of 5.5. And a 6 followed by a 6 is a mean of 6. So what you should see here is that all the possible means range from 1 to 6 in increments of 1/2. And the highest possible mean is a 6. You should also see that there are 6 plus 6 plus 6 plus 6 plus 6 plus 6 or 36 different outcomes. Different samples. But those means don't all occur at the same frequency. For example, there's only one way to get a 6. And there's only one way to get a 1. So for those two in our frequency table, or our probabilities, those probabilities are going to be 1 divided by 36. And for our sample, 6 only occurs once, so that's also going to be 1 divided by 36. Now, if we go up here and count the ways you can get a 1.5, there's 1, 2. So that frequency is 2 over 36. Or you could reduce it to 1 over 18, but we're just going to leave it at the number of counts over 36. So then the number of ways you can get a 2, 1, 2, 3, is 3 over 36. And the number of ways you can get a 2.5 is 1, 2, 3, 4. And the number of ways you can get a 3 is 1, 2, 3, 4, 5. So I'll just keep listing these. The number of ways to get a 3.5 is 1, 2, 3, 4, 5, 6. So we list that as 6 over 36. And then we count the 4s, 1, 2, 3, 4, 5. So we have 5 over 36. And then what happens because of symmetry, without me counting all of these, is that this one is going to be 4 over 36. You can verify that. And this one is going to be 3 over 36. And this one's going to be 2 over 36. Which gives you 36 over 36, which is 1, which is what it should be. So for example, here's those two 5.5s. And here's your 1, 2, 3 5s, and your 1, 2, 3, 4 4.5s. That is your probability distribution for the population's means if you choose the samples in twos. Okay? What you should notice, and we could draw the histogram if we wanted to, but what I want you to notice is that your frequencies, if we went back to frequencies instead of probabilities, or your probabilities, starts out low, builds to a high, and goes back to low. So the point here is that those means have a bell-shaped distribution. And the highest one is 3.5. And the lowest ones out here are the 1s and the 6s, and everything else is someplace in between. So everything that we've said about the means of these samples, even though the population was a uniform distribution because we had one of each one of these numbers, we took samples of size 2, the means followed a normal distribution. This is an example of the sampling distribution of sample means. Okay? Now what I want you to understand is that there is a big difference. This is the mean of all those sample means. I'm going to write mu x bar because we're talking about sample means. And that is the entire population over there because there's nothing else that can happen. So the mean of that sampling distribution is 3.5. Now let's go back up here and talk about the mean of the population. Here's our population. And let's just use the calculator to figure this up. So we're going to edit some data. I'm actually going to just clean out list 2. I'm going to clear that one out and just go in list 1. And our population is 1, 2, 3, 4, 5, 6. And I want to find the mean and standard deviation of that population. So I go to Stat and over to Calc and I choose 1 bar stats and choose list 1. Oh wait, sorry. Which it would default to anyway because I only have 1 list of data, but I'm going to choose list 1 and hit enter. And it says the mean, which is mu, 3.5, even though it says x bar, we know this is a population, so it's mu. And our population mean is identical to the sample mean. Okay? But our population standard deviation, we're going to choose the sigma equals 1.7078 because this is a population. So I want you to make a note of that. Now we're going to come down here and do the probability distribution. Is that far enough?
Yes.
So we're going to enter the probability distribution into 2 lists. So I'm going to use list 2 to be the sample means. Okay? Now these are not X's, they're not individual members of the population. These are the means of samples of 2 members of the population, pulled out 2 at a time, and all of them are represented. So the first mean is 1. Second one is 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, and 6. That's the highest one we can have. And then we'll enter the probabilities for each one of those means, the relative frequency of those means, because probability and relative frequency in this case are the same thing. This is actually going back to chapter 5, doing probability distributions. So So the first one is 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36 probability for the 6. And if you remember in chapter 5, we said we could go with our x values in list 1 and our probabilities in list 2, we could calculate the mean and standard deviation of the probability distribution. So we could go to stat and over to calc and choose one of our stats, but this time we have to give it where are the x values and then the list where the probabilities are. So that's going to be second and 2 because that's where I put the sample means, and then a comma, and then second and 3 because I put their probabilities in list 3. And I hit enter and it gives me the statistics. Now notice it knows this is a probability distribution because it doesn't give you a sample mean. It knows that a probability distribution is a population. So it tells you that the mean of the population is exactly what we knew it was. It's the number that's in the middle because it's in the middle of the distribution. So we're going to compare for the sample means distribution. Which is also a population of itself, but it's a population of sample means. This is a population of individuals. And our sample size is 2, remember here. That's important. It tells us that the mean of those sample means is 3.5. But what does it say about the standard deviation of those sample means? Does it match the population standard deviation? No. Is it larger or smaller?
Smaller.
Okay. 1.207. And 6 will be far enough. I'll just put some dots there. So it's smaller. Now what the central limit theorem says, and this is not in your notes, but I'm just going to give you an idea. What the central limit theorem says is that the larger your samples are, the smaller the standard deviation of their means. In other words, if I went back and took samples of 5 and listed out all the samples of 5, there's a whole bunch of them, a lot more than 36. But if I took all the possible samples of 5, which I could do, I could stand there and tediously list them all out and make this kind of frequency distribution, what would happen is that this value would still be 3.5 because the mean of the population is the same as the mean of the sampling distribution. But the standard deviation, the larger this gets, the smaller this is going to get. Now I'm going to go ahead and kind of pull the veil off of the hidden part. This value is actually the population standard deviation divided by the square root of the sample size. So if I take that 1.7078, and that's not all of the decimals, but if I take that and divide it by the square root of 2, which is my sample size, I get 1.20759, which is pretty darn close to 1.2076. Now, if I had used all the digits, so just for the sake of argument, I'll take that 1.707 and I'll divide that by the square root of 2. Oops. I get exactly the same thing. That's what the standard deviation is for the sampling distribution of sample means. And once again, you can probably understand quickly that if I put in a bigger number than 2, like maybe 10, then it's going to make that value shrink. And if I put in, let's say I had samples of size 100, well, that's going to make that value drop down to 0.1707, which is a lot different, a lot smaller. So the idea behind this, we're going to go back to the PowerPoint now. Is that if you have this sampling distribution of the mean, this is a population. And the mean of that population turns out to be the mean of the population of individual values that those samples were generated from. But the standard deviation of those means is a lot smaller than the mean of the population, or the standard deviation of the population, I'm sorry. So this is going to lead us to make some conclusions here. If X is a random variable with a normal distribution, and the mean is mu and the standard deviation is sigma, and that should say X bar, let X bar be the sample mean corresponding to random samples of size n taken from the distribution. This is what the central limit says. Central limit theorem. The X bar distribution, the distribution of sample means, is a normal distribution. The mean of the X bar distribution is mu. And that's the same mean as the original distribution or the original population. The standard deviation of the X bar distribution, and be sure you put bars over both of those X's, is sigma divided by the square root of n, which is the standard deviation of the original distribution divided by the square root of the sample size. It has a special name. Its special name is called the standard error. So I'm taking my notes to give you time to keep yours taken. This is where you should be. The X bar distribution is a normal distribution. The mean, which is mu sub X bar, of the X bar distribution is mu, the same as the original distribution. The standard deviation of the X bar distribution is sigma over the square root of n. And that's called the standard error, and its symbol is sigma x bar. And we can use that piece of information to draw some conclusions. The conclusions we draw are going to be about the means of samples from normal distributions, and if the original distribution is normal, then the sampling distribution will also be normal. Normal population, distribution of sample means from that population will also be normal. If the original distribution is not normal, then the sampling distribution is still going to be normal for large sample sizes. And notice there's quotes around that word large, because I want to stop and ask you a question here. Was our sample from our population, was it large? No, it was only 2. Was our population normally distributed? Look back at the population of the dice throw. 1, 2, 3, 4, 5, 6. Each one has equal probability. Would it be normal, or would it not just be uniform because they all have the same probabilities? So our original population actually had a uniform distribution. Our original population, let's draw some pictures here. Well, actually, better still, we'll look at it on the calculator. That will be a better way to do it, because the calculator will make histograms. So I'm going to go to the second, y equals, choose plot 1, press enter to turn it on, go down to the choice of graphs, and I'm going to go over to my histogram, and I'm going to make it from the data in list 1, which is my population. And then I'm going to go to the window, and since my population starts at 1 and ends at 6, I'm going to set the window up to go from 1 to 6, and I'm not going to have any negative probabilities or negative counts. Everything actually shows up one time, but I'll go up to 2 just to be sure we can see everything. Actually, no, I don't need to go up anywhere that far. All the probabilities is 1, so my X scale will be by 0.1, or actually we can do it by 1 divided by 6. And make sure there's nothing in y equals, and there's not, so I'm going to hit graph. There's the population. 1, 2, 3, 4, 5. Okay, we're not going quite far enough, so let me adjust my window a little bit more. Let me have it go from 0 to 7 so we can see all of them. So there's your 6 bars. X equals 1, X equals 2, X equals 3, X equals 4, X equals 5, X equals 6. Okay? And they all show up an equal number of times. But if I leave the window right where it is, and I go back to the stat plot, and I tell it, instead of using my X list as list 1, I'm going to use list 2. That's where those sample means are. And my probabilities or frequencies are in list 3. Look at the difference in my histogram. Very different. Is that a normal distribution? A symmetrical distribution, bell-shaped? Yeah. So even though my population wasn't normal, going back to the PowerPoint, my population wasn't even normal, and my sample wasn't even large. But my sampling distribution of means was still normal. So that second part is really a very strong statement. It seems to say that you have to have a really big sample, but in our case, we didn't have, and yet it still worked. Now, I can tell you the reason that it did. The reason that it did is because our population was itself symmetrical. Not normal, but it was symmetrical. Because things that are a square box, if you fold them in half, the right half of the box looks just like the left half. So the fact that it was symmetrical actually promoted it being more normal. So the key things to remember here, these are your symbols. The mean of the sample means is called mu, but it has a little X bar after it to denote that it's the mean of the sampling distributions of X bars. The population is sample means. And it's equal to the population mean, mu. It's equal to the mean of the original distribution. In the third conclusion, the standard deviation of the sampling distribution is actually called the standard error, because it gets confusing to keep saying the mean of the population or the mean of the original population and the mean of the sampling distribution of sample means. Because we're going to get really tired of saying the mean of the sampling distribution of sample means. So to make a distinction between those two standard deviations, if we're talking about sample means and their standard deviation, we're going to call that the standard error, just so that we don't have to say so many words. But the standard error is equal to the population, the original population standard deviation, adjusted by dividing by the square root of the sample size. And as those samples get bigger, their standard deviation or standard error is going to get smaller. We can calculate z-scores just like we did before. Our z-score formula really hasn't changed, except that our members of our population are now x bars, not x's. And we're going to subtract the mean from that and then divide by the standard deviation of the x bars, which is sigma over the square root of n. So we're going to do an example. And I'm going to work this example with you so that you can see how things change and how they don't. Because some things do change, but not everything changes. So our first example says that the time it takes to drive between cities A and B is normally distributed with a mean of 14 minutes. And a standard deviation of 2.2 minutes. And our first question says, find the probability that a trip between those two cities takes more than 15 minutes. So that single trip is a value of x, the travel time. And we're trying to find the probability that x is greater than 15 minutes. So by what we know, the mean of this is 14, and it says the standard deviation is 2.2. So that means the next mark up would be 16.2, and the next mark up would be 18.4, and the next mark up would be 20.6. And then going down, 14 minus 2.2 is 11.8. 11.8 minus 2.2 is 9.6. 9.6 minus 2.2 is 7.4. So virtually all the travel times, 99.7% of the travel times, are between 7.4 and 20.6 minutes. And that's for individual trips. And then our question says, what's the probability an individual trip takes more than 15 minutes? Well, 15 minutes is only a little more than 14. So it would be right there. And the probability of it being greater than that would be this area here. Is it fairly likely that the trip might take more than 15 minutes? Yeah, it has a substantial probability. And we would find that probability by going to normal CDF and going from 15 to positive infinity with a mean of 14 and a standard deviation of 2.2. We did that on the last test. And it says that probability is 0.3247. Which is 32.47%, so it's fairly likely. And that should make sense, because if we go back up here and calculate that z-score here in a minute, the z-score for 15 is 15 minus 14 over 2.2. And that's a z-score of only 0.45. And if you look at it, that kind of makes sense, because this is not very far above the mean. And the mean has a z-score of 0. So that 15-minute trip is less than a half a standard deviation above the mean. So that's why that probability is so high. But now we're going to look at it a little bit differently. Let's go to problem 2. It says find the probability that the mean time, not one trip, the average of a bunch of trips, the average of 9 trips, so n is going to be 9. And find the probability that's more than 15 minutes. So notice what's different. This is important. Notice what's different. This was 1 trip. X was greater than 15. This is 9 trips. The mean of 9 trips. That's an X bar is greater than 15. Now before I go any further, what I want to do to make sure you understand the difference here is now we have a sample size and we have a value for X bar. So we're going to go back up here and recalculate a Z-score so you'll see the difference in the Z-scores. And when you have that X bar, it's important that you also bring along your sample size. So our formula over here, we're going to use that one. So Z is going to be X bar minus the mean, which is still 14, divided by the standard deviation, which is 2.2, over the square root of 9. So notice what changed. This did not change. What changed was the denominator. And just to make sure, I'm going to put some parentheses around this. So our Z-score now is 1.363. So when we come down here to our curve, this curve does still have the same mean. It's 14. And that Z-score would still be 0. But the Z-score for our sample now is going to be 1.36. Is the probability going to change? Just looking at the two pictures, does the probability change? Changes substantially. And we're going to find the probability just like we did before. Still going to use normal CDF. We're still going to start at 15. We're still going to go to infinity. We still have a mean of 14. But what changes is that we use 2.2 divided by the square root of 9. Let me clear the rest of that off there. The probability now is only 0.08634. Which is only about 8.63%. Okay? Now, have you had to trash everything you learned in chapter 6 up to now? No, it's still the same calculator command. The only thing you need to look for is one word. One word in the problem. What is that one word you need to look for? Mean. You need to look for the word mean. And as soon as you see the word mean, then you know that you should be looking for a sample size. Because if you've got a mean, you had a sample. And you need to know how big that sample was. That's the only thing you need to worry about. Okay? Now the only thing that we need to worry about is, well, okay, this one told us the population was normal. What if the original distribution isn't normal? If the original distribution isn't normal, you use the central limit theorem. And what the central limit theorem says is what we've been talking about this whole time. I just repeated it there. It says basically it doesn't matter how x is distributed, as long as the x's have a mean mu and a standard deviation sigma, the sample based on the sample mean based on a random sample of size n will still have a normal distribution as n gets larger and larger and larger. We've already seen that n of only 2 for the population we looked at, it worked. So we're going to assume that we can do it. And then if you go on to the top of your next page, it says, how large does n need to be? Well, in most cases, a size of 30 or more will assure that the distribution will be approximately normal. Now, 30 is not a magic number. It just happens that if your sample has at least 30, then when it says approximately normal, no, it's absolutely normal. It really is. This is a very, very strong theorem. What we will learn in the next chapter is that if we don't have a key piece of information, we can still use the same ideas we're using now. The only difference is that we're going to have to use something that's not a z-score. In chapter 7, we're going to use something called a p-score, which works the same way. Okay? But for now, we're just going to work an example. This is just a repeat of the central limit theorem. So this is the application that we're going to work here in class right now. So our first problem says record, well, actually the only one we're gonna do, I don't think we have but one. Yeah, we don't have but one more example. It says that packages shipped by a certain trucking company I'll find my highlighter. By a certain trucking company have a mean weight of 510 pounds. Now, is that a mean of a sample or is it the mean of a population? That's the mean of a population. And it says it has a standard deviation of 90 pounds. So that's the standard deviation of the sample. And then it says 100 packages are being shipped today. What is the probability that the mean weight will be more than 530, less than 500, and between two other numbers? What was the key word we were looking for? Mean. So that's what's changed. We now have X bars. When we have a mean, what do we need to know besides the value of the mean? What do we need to hunt for immediately? If it's a mean, what do we have to have? We needed a sample, so we must have a sample size. What's the sample size? 100 packages. Okay. So now we can start working the problem. Mu is going to be 510. But what I want you to take into account is that each one of these little increments here is no longer 90, because this is the sampling distribution of sample means. So each one of these is worth 90 divided by the square root of 100. And that's just 9. Because 9 divided by 10, or 90 divided by 10 is 9. So this first mark is 519, and then 528, and then 537. So when we're looking at those increments, we're looking at sigma x bar, the standard error. You mark off your curve in standard errors this time, because you have a sample mean and you have a sample size. And that tells you then that your 530 isn't really close to the center. Your 530 is up here. So is it going to be really likely that the weight of that 100 packages is going to be more than 530 pounds? No. Sure isn't. And we can find it just like we did before, normal CDF. We're going to start at 530. We're going to go to infinity. The mean of our distribution is 510. The only thing that's changed is we're not going to take the original population standard deviation alone. We're going to call it 90 divided by the square root of 100. So I'm just going to go back and edit this one into what I want it to be. So 530 to infinity, the mean is 510. And the standard deviation was 90 divided by the square root of 100. So my probability, just like you said it would be, is very small. Very small probability. So if that happened, they should be upset. Yes.
So, if I'm wrong, tell me I'm wrong. Basically what we're doing, different than what we have before, is we're looking for just a mean probability. So we're just going to divide the deviation by the sample size.
Square root of the sample.
The square root of the sample size, sorry.
No, that's correct.
So that's
That's
the
it.
only variation.
That's the only variation. That's correct.
So nothing has changed, just how we're finding the deviation.
Exactly. That's all you're doing. Once you see that word mean, start looking for a sample size, because you know that mean means there was a sample. So you look for a sample size, and you just kind of like tack that on, take the square root of it and tack it on the end of your normal CDF. And it's all good. Okay? So let's do a couple more, and then you've got a worksheet that you can do for practice, so that I can check and make sure you've got it. So again, the only thing that's changed, 510 still in the middle, but we're going to use 90 over the square root of 100 is our standard error. So that means this is 519, 528, 537. And if we're going to go down, 510 minus 9 is 501. Minus 9 is 92, or 492. Minus 9 is 483, if I did my arithmetic right. So when this says the probability is x is less than 500, well, 500 is right about here. And that means the probability that we're looking for is this probability, which again is very small. So we're going to go from negative infinity to 500 with a mean of 510 and a standard deviation of 90 divided by the square root of 100. That's the only thing that's changed, that very last part. So there's your command. Normal CDF, negative 1E99, 500, 510, 90 divided by the square root of 100. And again, when we do that, you should be expecting an answer that's relatively small. And it's only 0.1333. Which is about 13.33%. Any questions? Okay, then we're ready to do our last one. Still have the same distribution. And this one says between 495 and 515. 495 is somewhere between 492 and 500, probably right about here. $5.15 is between 5.10 and 5.19. So we're going to get a little bit larger probability this time. Mm-hmm.
Put in the 90 divided by square root of 100. Can we just put 10?
You can put 90 divided by 10. The only reason I keep doing it that way is because if you have a weird sample size like 23, then you don't want to round anything off. You want to actually use the square root of 23.
Okay.
But yeah, if it's something you can easily take the square root of and do that, that's fine.
All right.
So that one does turn out to be a little bit bigger. It's about 0.6629, which I would round to 0.6630. Or 66.3%. So is everybody okay with this? Check what you put in. Just hit second enter, you should be able to go back to it. Yeah, it's easy to leave something like that out. Okay, for your homework. You can have this in front of you. If you need little hints to help you along with this, that's what that last page is all about. It's kind of like a process that you follow. Here's your practice. And this is due by next class period. Be on the lookout for sampling distributions. There's several pages of this. Remember, if you see the word mean, you need to use the sample size to fix your standard deviation. If you don't see the word mean, then it's just regular normal CDF.
So sampling distribution is not a normal distribution, right?
Yeah, the sampling distribution is a normal distribution, but it has a smaller standard deviation than the original normal distribution did. Okay? That's the only thing that changes. Its standard deviation is smaller. And there are several pages of these for you to practice. I think there's like 8 or 10 problems. Yeah, there's 10. So be sure and practice those so I know for sure that you've got this. That's your homework assignment. Now, in order that you know what's going on, yes ma'am, before we go on.
On this homework, you want us to draw the things?
Normally I would say yes, you have to. It does increase the likelihood that you'll actually get the problem right. But as long as you're getting correct answers without drawing it, you're okay. Unless I specifically tell you you have to draw the curve or I put one there, you don't have to. This same one? No, I thought it was a different one. Hang on. I didn't realize I'd already posted it. Let me check. I knew that I was going to do it, so you may be right. I may have already done it. Which folder is it in, Leslie? Oh, chapter 6 homework, maybe? Oh, I forgot I changed the name of it. Yeah, it's the same as worksheet 5. Just whatever you did for worksheet 5, go ahead and load it up into the last folder so I can give you a separate grade for it. And I'll leave it here, but you don't have to turn it in here. You actually can turn it in the other folder. I didn't realize I put it in there twice. Let me see if I can rename it. So you just have 2 copies of it. It's in the chapter 6 homework. You can turn it in the other folder. That way you don't have to be trying to go all over the place. Thank you for bringing that up, Leslie. I appreciate it. Okay, there you go. So you don't have to put anything in there. It won't be graded.
I don't know how to ask this, just to ask, so I have to show you.
Okay.
Okay, so you had showed me that before, which of course that's what we went over today. So when I did that, this is what I got. So when we do this, how many places are we rounding?
Just one, because that's probably the best you can do in most cases.
Okay.
Okay. Okay. I've got one extra copy, Leslie printed off an extra one if anybody needs a paper copy of the practice. Okay, let's go into Chapter 7 warm-ups because I want to give you an idea of what's coming up in the next chapter. And I'm still going to relate it to what we've already done. But I am going to give you a little up front. Chapter 7 will be much easier to do because we are not going to do it with formulas. In Chapter 7, there is a routine in your calculator that already has things built into it where you can go and ask for confidence intervals. And that's what Chapter 7 is about. It's about confidence intervals. Chapter 8 is about hypothesis testing, which is related to confidence intervals. And Chapter 9 is a continuation of hypothesis testing, but it's the comparison of two means, whereas Chapter 8 is not comparing two means, it's only talking about one. So Chapter 7, 8, and 9 are all going to be done completely on the calculator. The key to your understanding how to do these problems is going to be being able to read the problem and pick out the information that you have.
What you said the difference was between 8 and 9 is hypothesis testing?
Hypothesis testing in Chapter 8 is from one sample from one population. And in Chapter 9, it's from two samples being compared from two different populations. That's the real difference. But every process we do from here on out is going to be on the calculator, and you are going to have to interpret the answer. There is no math to do. None. No arithmetic. But you have to be able to interpret the answer, which is why I'm doing this.
Drawing conclusions?
You're going to have to be drawing conclusions. So what's happened, once we pass Chapter 6, in Chapter 1, 2, 3, we studied about descriptive statistics. What is the purpose of statistics? What do they look like? How do you get them? How do you generate them? In Chapter 4, 5, and 6, we talked about probability. And the main thing you should have taken away from that whole section on probability is that if the probability is closer to 1, it's more likely. And if the probability is closer to 0, especially if it's less than 5%, it's not likely. It's very unlikely. Because that will be the basis for everything we do in Chapter 7, 8, and 9, whether or not something is likely to have occurred by chance. Okay? So we're into the area of statistics now called inferential statistics. If there's any business majors in this class, you need to sign up for Math 2080 next semester if you are a university parallel business major. Now, if you're not sure, then you need to check with me and let me look up your major on the computer for you. But Math 2080 is inferential statistics for business, and it is a once a year offering. You only get to take that class once a year. But you need to be in the University Parallel TTP to take that class. Otherwise, you don't need it. And if you're going, it depends on where you're going. So if you're not sure if you need to take it or not, please ask. But be aware that if you are going to need to take it, you want to go ahead and take it next semester while this is still fresh on your mind. So here's your Chapter 7 warm-up. I've already got it printed off for you. There is no PowerPoint that goes with this. I think Scott went over these formulas or some of these formulas with you at the beginning of class in 0530, those of you that were there. I know he went really fast.
I took a picture of this one.
Okay. Well, this probably looks familiar then. This E is not called standard error, it's called margin of error. This is how you calculate it, by that formula. Since this is inference, we are not going to have the population mean because we rarely have the population. What we will have is a sample drawn from the population, and we'll have its mean. We're going to assume it's a random sample, and therefore its value should be close to, even though maybe not exactly equal to, but close to the value of the population mean. We're going to use that sample's mean along with either the value of the population standard deviation, if we know it, or the value of the sample standard deviation if we don't know the population standard deviation. And we're going to calculate the margin of error by choosing a level of confidence, which will give us the z-score. This will be a z-interval where there's a negative z-score to a positive z-score. And the standard deviations will tell you what the margin of error is. So your confidence level is going to tell you that it's 2 margins of error wide. Okay? It still relates back to a normal curve. Most of what this is for is to get vocabulary before we actually go to the calculator. If you need the z-score, we're going to get it using inverse norm. You've done that before. All you need to know for inverse norm is the area in the tail of the distribution. And that area is referred to as alpha over 2. That little fishy looking thing is an alpha. It's a Greek A. Alpha over 2 is based on the confidence level, which we're going to call C. In order to find alpha over 2, you're going to take 1 minus your confidence level, which is going to give you the area in between the two z-scores. And then you're going to divide that by 2. Now I'm going to show you how to do that here. And then we're going to use all of this information to work these problems. So all you're going to be doing right now is listening and copying down. And the only thing we're going to use the calculator for is arithmetic. So the first one says find the critical value z alpha over 2. Notice that vocabulary word there, that's critical value. That corresponds to an 80% confidence level. This is what that means. You have a normal curve. It's based on z's, so the center of it is going to be at 0. And you're going to have a z-score on each end. One of them is negative, one of them is positive. And this 80% confidence level that it's talking about is the 80% of the curve that's in here. So that part that I colored in is 80%. Or 0.8000. Now, if you have 0.8000 from here to here, how much is in here? Okay. Yeah, 10% or 0.1. Because 1 minus your 0.8, and then divide that by 2, is alpha over 2. And 1 minus 0.8 is 0.2 over 2, which is 0.1. Okay? If there's 80% in here, there's 10% here and 10% here. When you're trying to find the critical value, these are exactly the same number. The only difference is one's positive, one's negative. So we're only going to find the lower one. We're going to find the one in the bottom. And that's how we're going to find it. We found that in chapter 6. So that z-score is negative 1.2815. Or 1.5, not 5, 1.5. So we're going to say that the z critical value, that's why I wrote z sub c. Z sub c is equal to plus or minus 1.28. This one is negative 1.28. This one's positive 1.28.
And that's all we do?
That's all you do to find the critical value. That's called a critical value. Okay? I'm going to slide up a little bit. We're going to work an application problem. So the first thing we're going to do is we're going to read the problem and gather information. It says a simple random sample of 45 birth weights. What is the sample size?
45.
Okay. What variable do we use to represent sample size? N. So there's our first piece of information. Has a mean of 3,250 grams. Is that mu or is that X bar? How do you know?
Because it says it's a sample.
It says it's a sample. Therefore, it's an X bar. So that's 3520. And the standard deviation of all birth weights what's the symbol? All birth weights, is that the population or the sample? That's the population. Therefore, that's sigma is equal to 500 grams. So there's 3 pieces of information so far. You're going to construct a 99% confidence interval. Your confidence level is 0.99. Okay? Now I'm going to use that information to draw a picture down here toward the bottom. That's a very lopsided curve. This is the assumption. Your confidence level is 99%. That's 99% from here to here. It is centered over the mean of a sample which is 3520. These two z-scores are based on the value of the amount that's in that tail. How much area is in this tail? Point.
It's 0.05.
Well, that's it.
Is it 0.05? Point 0.05 is 5%. What's in the tails? Half of 1%.
Oh, 0.005.
0.005.
So we were both wrong.
That one's the one that's tricky. That's why I went ahead and put it on here now. If it's 99% out here, you need to remember that that's half of 1%. And half of 1% is 0.005. If you're not careful, that one thing will mess you up all the way around. Okay? So what we need then is we need the z-score that goes right there. This is the z-score for 0.005 in the lower tail. That means we need to find that z-score. Okay. For argument's sake, we will round that to negative 2.76. Now, in order to do the rest of what we need to do, we need to find the standard error for this distribution because that's part of the formula. because it's a z-score. We're looking for a z-score. The z-score in the dead center is 0.
On the other chapter, in the other chapter that we did, we not use the mean.
We're using X bar though, not mu, or they're using X bar, not mu, so that's why we don't put it in the understanding.
Well, it's not only that, but it's because X bar is at z is 0. What we're looking for is z-scores.
Okay.
Your critical value
I'm
is a
just on
z-score.
information overload right now.
Okay. Just remember that if it says z, the mean is 0 and the standard deviation is 1. Always, regardless of how you're using it. If you're looking for a z-score, the mean of z-scores is always 0 and the standard deviation of z-scores is always 1.
Okay.
Okay? So we're not talking about the sample at that point. We're talking about the z-scores, which are critical values.
Okay.
Okay?
Yeah, I'm with her, there's just so much.
Okay, let me explain to you what this z-score tells you. This z-score tells you that you are 2.576 standard errors below the mean. That's what it measured when it was counting standard deviations. It's still counting standard deviations, only now it's counting them as standard deviations of sampling distributions. Okay? It is, it's like fences. That's exactly what you ought to relate it to. So this negative 2.576 is based on that. Z of -1, -2, -3, and each one of these is a sigma over the square root of n. Okay, a standard error. So that means each one of those little green things is going to be 500 divided by the square root of 45. Okay? We take these two pieces of information together to get the standard error. And this may be where it starts to come clear to you, so watch carefully, okay? I am 2.576 standard errors, 2.576, below that sample mean, okay? So that negative 2.576 times a standard error that's not 500s. Oh, yeah, it is 500s, 45 sample size. Says that what I need to do is I need to take this 3520 and subtract 191.99, which I'm going to call 192. I'm going to round it to 192.
So why did we need to find that? Just so we can have that answer? Or
That's the lower edge of our confidence interval. That 192 is the same exact amount that's on this side.
oh, is that why, like, when it says B, find the maximum error, is that how we find the maximum?
That's how you find the
That's what
maximum
we're-
error. That's the maximum
Why
error.
we're doing this, because
Yeah.
I thought we already, like, were past all this.
No, no, no. So what we're finding right now, what we just found, was the maximum error of the estimate. The maximum error of your estimate is your z-score times your standard error. And the maximum error of your estimate turns out to be 192. And the reason it's plus or minus 192 is because one of the 192s is going to be added to that sample mean, and the other one is going to be subtracted from the sample mean to give you these two edges, these two fences or boundaries.
Okay, so on these, we have to work backwards to find these answers. So first we need to find the confidence interval, and then we'll be able to find the maximum by using E equals,
Z alpha over 2
Yeah.
times sigma x bar.
and then we find find the point estimate? Or,
I haven't told you what the point estimate is yet.
Okay.
So we're not going through the questions in order.
okay,
When we get done, I'm gonna link all these up for you, okay? So your maximum error of the estimate so that you'll see where it is in the picture, your maximum error of the estimate is there. Okay? The point estimate for the population mean is where you would think the population mean should be. Where do you usually find the population mean? In the middle of the curve. That's called your point estimate. Your point estimate for a population mean is a sample mean. A point estimate is like a best guess. Okay? Think of it as a best guess. If you didn't know the population mean, the best way to figure out what it might be, or the best guess for it, would be to take a sample from that population and find the mean of the sample. That should be close. Okay? The best guess for the standard deviation of the population, if you don't have it, because we had it, but the best guess for it would have been, if we had it, the sample standard deviation. That would have been a good guess. If we were looking for percentages, if we wanted to know what percent of the population voted in the last election, the best way to get it would be to take a random sample from the population and find out how many of them voted and get a percentage. Okay? So all point estimates are guesses, but they're not just wild random guesses, they're educated guesses. They're guesses based on some evidence drawn from the population. Now, when this says construct the 99% confidence interval, here's your, not quite. Here's your confidence interval. It's the value that goes here and here, but not in terms of Z, in terms of birth weights. So your confidence interval is going to be that 3520 plus or minus, because one of those margins of error is above, one is below.
Plus or minus the maximum error.
That's right. So it's plus or minus your maximum error. And that's E. And we know the value of E. That's 192. So we're going to take that 3520 and add 192 and subtract 192. So our confidence interval is from 3328 to 3712. Okay? Questions?
So that's how you write it, what if you didn't want to write all that, you just wanted to put the answer, if you put 3712.
Actually, the main thing is once you've got these numbers is to interpret what that means. So that's going to be the last part of this, and for that I do not need a calculator.
Isn't it just like a sentence?
It's a sentence. And it's a really easy sentence because it always says the same thing with different numbers in it. It says, we may be 99% confident or 99% certain that the mean of the population of birth weights, you need to take it back to the original problems, is between 3328 grams and 3712 grams. Okay, that's your entire problem right there. Now, we're not going to get to the second part of this. Because right now I'm not worried about this second part. I wanted you to get this part. Okay? We will come back to this. We are not going to finish this necessarily at the beginning of next class period. We will come back to this. What we're going to do at next class period is I'm going to show you how to use your calculator and pick out the information and come up with those two numbers with no work on your part. The only work you're going to have to do is picking out all the information that you need to feed the calculator. Okay? So don't try to work on the Chapter 7 warm-up any further. Hang on, let me work on it with you. But do the practice for Chapter 6. You need to be done with Chapter 6 because we're going into Chapter 7.